When historians describe the year 1898 across American industrial centers, they usually focus on the mechanization revolution above ground, the expansion of factory assembly lines, the installation of steam-powered machinery in textile mills and manufacturing plants, the rise of scientific management and time-motion studies to optimize human labor, and the 560 new manufacturing facilities opening annually as America transformed into an industrial powerhouse. But the real story, the one that barely appeared in industrial journals, the one that even today sits buried in demolished factory foundations, began inside the production machines themselves. It started with a straightforward factory efficiency survey. Industrial engineers were instructed to assess manufacturing operations across Massachusetts, Connecticut, and New Jersey for potential productivity improvements. The goal was practical: document production rates, identify bottlenecks, and determine whether factories could increase output through better supervision and worker training. But the moment survey teams began examining the older manufacturing equipment, the machines installed between 1840 and 1870, something unexpected happened. They discovered automated production systems that required no human operators at all. Throughout the surveyed factories, in equipment predating electric motors and control systems, the crews found self-regulating machines and autonomous production lines that adjusted their own operation without human intervention. Their performance was documented in decades of production records. Their consistency was undeniable, and the technology didn't resemble anything in the industrial equipment catalogues of the era. It didn't even resemble European factory automation as commonly understood. This wasn't mentioned in the public reports about industrial efficiency. It didn't make it into the newspapers covering manufacturing growth, but in the internal notes of that year, a quiet phrase appears over and over again. Pre-existing automation systems, self-regulating operation, control mechanism undetermined. The official story would later simplify all of this into well-designed mechanical governors, skilled operator adjustments, creating the illusion of automation, or simply exaggerated production claims by factory owners. Nothing unusual, nothing worth discussion. But the survey photographs from the time, the ones developed in consulting firm offices, while America expanded its industrial workforce, show something different. They show engineers examining production lines that maintained precise tolerances without operators, manufacturing equipment that detected defects and corrected its own operation in real time, quality control systems that sorted products, adjusted machine settings, and even shut down production when materials ran low, all through purely mechanical means, with no electrical controls, no human supervision, and no computers. And the deeper they investigated, the more the machines stopped looking like simple mechanization as we know it, and more like true artificial intelligence implemented through gears, levers, and pneumatic systems. Autonomous production technology that had been operating in factories for decades before electronic control systems, achieving performance levels that modern automated manufacturing struggles to match even with advanced sensors and programmable logic controllers. At first, the survey teams tried to categorize everything in the simplest way possible. Well-trained operators making rapid manual adjustments that appeared automatic, clever mechanical linkages that coincidentally produced consistent results, exaggerated claims about machine capabilities by factory owners proud of their equipment. But as documentation accumulated and more factories were examined, the inconsistencies multiplied. Why were some of the production machines built with feedback sensing systems far more sophisticated than simple mechanical governors? Why were certain manufacturing lines capable of detecting dozens of different error conditions and implementing appropriate corrections for each, all through mechanical logic without any human decision making? Why did some equipment demonstrate learning behavior, improving its own performance over time through mechanical adjustment systems that appeared to remember and compensate for recurring issues? and the question that troubled even the most experienced industrial engineers. Why were these systems so reliable? Early 20th century factories struggled with quality control, requiring armies of inspectors and supervisors. Yet production records showed the older self-regulating machines maintaining tolerances of almond 1,000th of an inch, achieving defect rates below 0.1%, and operating continuously for weeks with zero human intervention. Performance that factories with hundreds of workers and modern supervision couldn't match. Survey teams quietly admitted among themselves that the operational characteristics didn't line up with any known automation method. And although none of them were using terms like mechanical artificial intelligence, they were acknowledging something just as unsettling. Someone had developed technology to create truly autonomous machines, not through better supervision, not through skilled operators, through mechanical systems that could sense, decide, and act independently. If you're finding this investigation compelling, consider subscribing. These mysteries don't fit neatly into official history, and uncovering them requires looking where conventional narratives refuse to go. As the documentation increased, so did the corporate intervention. Equipment manufacturers accelerated machine replacement schedules. Engineers who documented the sophisticated self-regulating systems found their survey reports rejected or heavily edited. Factory owners were pressured to modernize their production, meaning replace autonomous machines with newer equipment requiring constant human supervision and adjustment. And then the most sophisticated installations were systematically dismantled during factory reorganizations in late 1898 and throughout 1899, scrapped where needed for workflow optimization, and much of what was documented was destroyed before independent researchers could conduct proper analysis. Only fragments remain, survey notes with critical sections missing, a handful of photographs in private collections, and the quiet testimonies of factory workers who operated alongside the machines before management ordered demolition. But even from what survives, a pattern becomes visible. Automation technology too sophisticated for any known method. Machine intelligence too advanced for the accepted timeline. Control principles that look perfected rather than discovered. And occasionally, buried in abandoned factory foundations, components of the original systems, corroded mechanical logic, units, pneumatic sensing arrays, feedback mechanisms that even today's engineers struggle to understand. When the survey teams moved beyond the first recognizable modern manufacturing equipment in newer factories, the expectations were simple. They believed they would find steam-powered machinery, perhaps some early mechanical automation, and production processes heavily dependent on skilled human operators. Nothing unusual, nothing extraordinary. But within months, that assumption collapsed because, instead of a straightforward progression from manual labour to supervised mechanization, the teams uncovered machines that operated with a level of autonomous intelligence that made contemporary supervised production look primitive and inefficient by comparison. The first anomaly was adaptation capability. In manufacturing systems throughout the surveyed regions, engineers found production equipment that automatically adjusted to variations in raw materials. Not simple compensation for obvious differences, but sophisticated adjustment. Machines that detected subtle changes in metal hardness, wood grain direction, textile fibre quality, and automatically modified cutting speeds, feed rates, and tool pressures to maintain consistent output quality. Different automation levels shouldn't do that. Simple mechanical governors responded to speed variations. Skilled operators adjusted for material differences. But automatic detection and correction of dozens of variables simultaneously through purely mechanical means shouldn't be possible without sensors, computers, and control systems. Yet throughout older factory districts, it was. Manufacturing equipment in Massachusetts textile mills showed identical adaptive capability to machines in Connecticut's toolworks. Installations built by different manufacturers in different decades demonstrated the same remarkable autonomous intelligence even when producing completely different products. It was as if every machine builder working between 1840 and 1870 understood an original automation principle, one that no longer existed in any engineering manual. As the workers investigated deeper into the machine internals, the technology became stranger. Beyond the expected gears, shafts, and steam cylinders, they began encountering systems that looked nothing like conventional mechanization. Pneumatic logic circuits that performed Boolean operations through air pressure patterns, mechanical memory systems that stored production parameters and recalled them when needed, sensor arrays that measured dozens of production variables simultaneously and fed them into decision-making mechanisms composed entirely of levers, cams, and valves. Some systems appeared almost over-engineered. Feedback control mechanisms with multiple cascading stages crafted with precision that didn't match the crude machine tools attributed to that period. The components themselves raised questions. Metallurgical analysis conducted years later on salvaged parts showed manufacturing precision exceeding what machine shops of the era supposedly could achieve. Bearings with tolerances of 0.001 inches, pressure regulators maintaining stability to fractions of a psi, pneumatic valves cycling millions of times without wear. And then came the discovery that puzzled even the most conservative members of the engineering community: true machine learning through mechanical means. Not simple adaptation, but actual improvement. Machines that analysed their own performance, identified patterns in defects or inefficiencies, and physically reconfigured their internal mechanisms to eliminate the problems. Survey documentation described production equipment that became more accurate the longer it ran. Machines whose first products after startup showed measurable variation, but whose output after weeks of operation achieved precision that skilled machinists couldn't match manually. The equipment appeared to be practicing, refining, perfecting its operation through entirely mechanical feedback systems that modern engineers struggle to explain even after examining salvaged components. Yet there is no historical record of any American factory having machine learning capability before 1898. No patents showing any inventor achieving autonomous improvement through mechanical systems. Nothing that explains why manufacturing equipment across multiple states exhibited behavior that anticipates modern adaptive control, operating through purely pneumatic and mechanical means, decades before electronic computers and programmable controllers were even conceived. Survey photographs taken in 1898 and 1899 show this clearly. Engineers standing beside production lines with no operators in sight, yet producing perfect components at high speed. Mechanical logic systems with hundreds of interconnected elements performing decision-making functions. Pneumatic computing assemblies that processed multiple sensor inputs and generated appropriate control outputs, all without electricity, all without human intervention. But the most unsettling detail was not what appeared in the photographs. It was what happened to factory production records themselves. Manufacturing logs from the 1850s, 1880s frequently reference autonomous operation, self-correcting machinery, and mechanical intelligence producing their output. But industrial histories published after 1900 systematically reinterpret these references as skilled operators or well-designed mechanical linkages, despite the original documents clearly describing unmanned operation and autonomous decision-making. The silence is hard to miss, because if these manufacturing systems truly represented only conventional mechanization, why weren't they simply documented as clever mechanical design? Why the urgent replacement of functioning autonomous equipment? Why were working production lines forcibly dismantled when they were achieving performance that supervised? Manufacturing couldn't match. Even the engineering evidence raised red flags. Machine complexity far exceeding structural requirements, pneumatic systems designed for information processing, not just power transmission, mechanical logic circuits capable of implementing complex decision trees, features that looked less like production equipment and more like mechanical computers. Computers that, according to the conventional timeline, didn't exist until electronic systems were developed in the 1940s, yet here they were, fully implemented and operating in factories of the 1840s. The deeper the team surveyed, the harder it became to fit these findings into the accepted narrative of industrial automation development. Because machine by machine, factory by factory, the older production facilities began to look less like a progression toward better mechanization and more like a systematic replacement of superior autonomous technology with inferior supervised systems. A transition that made no technical sense but perfect economic sense. If someone wanted to ensure factories remained dependent on large workforces that could be controlled, supervised, and kept in employment relationships rather than replaced by autonomous machines. When the survey teams pushed deeper into their examination of the self-regulating production systems, the discoveries stopped resembling anything that belonged to conventional industrial mechanization. What they began uncovering were not just automated machines, but complete autonomous manufacturing intelligence operating on principles that mainstream engineering wouldn't acknowledge until the computer age. Technology that didn't match known automation science, didn't match any patented systems, and somehow achieved capabilities that modern factories with PLCs and industrial robots struggle to replicate in terms of true autonomous adaptation. The first shock came with the complexity of decision-making. These machines weren't just executing predetermined sequences, they were making contextual decisions based on real-time conditions. Production equipment that detected when cutting tools were dulling and automatically adjusted feed rates to compensate, then scheduled its own tool changes at optimal times to minimize production interruption. Manufacturing lines that sensed when raw material quality was declining and automatically modified processing parameters to maintain output specifications, while simultaneously adjusting production rates to account for the increased processing time required. The sophistication wasn't theoretical speculation. It was documented, measured, witnessed by factory supervisors who kept detailed logs because they couldn't believe machines could operate so intelligently without human guidance. And then came the feature that still confounds industrial historians today: the cooperative factory networks. Officially, this was later dismissed as coincidental timing or exaggerated claims, but nothing about the documented behaviour fits independent operation. Factory records show that production machines across entire facilities coordinated their operation automatically. When one machine experienced a problem and slowed production, upstream machines automatically reduced their output rates to prevent buffer overflow. When downstream equipment needed a specific batch, upstream machines automatically adjusted their parameters to produce it without human scheduling. The machines communicated not through electrical signals or human coordination, but through mechanical and pneumatic connections that allowed them to share operational state and coordinate production as a unified intelligent system. Factory supervisors from the 1860s through 1890s described in shift logs seeing the machines thinking together, not poetically, but as the only explanation for manufacturing coordination they witnessed daily. Production lines that balanced their workload automatically, machines that sequenced their maintenance needs to minimize disruption, factory-wide adaptation to rush orders or material shortages that happened faster than human managers could even assess the situation and make decisions. Another anomaly appeared in the defect detection and correction systems. Individual machines showed impressive quality control, but the true sophistication emerged in how defects were traced back to root causes. Production equipment that not only detected when output quality declined, but automatically analysed whether the problem originated in raw material variations, tool wear, mechanical misalignment, or operating parameter drift, then implemented the appropriate correction for each specific cause. Many of these diagnostic systems were embedded so deeply in machine architecture that disassembly revealed mechanical logic circuits with hundreds of decision pathways, pneumatic computing elements that performed what modern engineers recognize as fuzzy logic operations, and feedback mechanisms that created learning loops, allowing machines to improve their diagnostic accuracy over time. It created an uncomfortable possibility. The self-regulating machines may not have been independent inventions by various manufacturers. They may have been components of a planned industrial intelligence infrastructure, a factory-scale autonomous system designed before individual machines were built, coordinated across multiple industries, implemented by an organizing authority that no historical record properly acknowledges. The deeper the engineers investigated, the more impossible it became to dismiss these findings as clever mechanical linkages. What emerged was evidence of systematic automation intelligence, a complete autonomous manufacturing capability that extended through at least 280 documented factory installations across 4 states, possibly more. Here's where the story gets truly bizarre. In the months following the initial surveys, documentation teams catalogued over 90,600 individual autonomous control elements within the surveyed machines. Not counting simple mechanical governors or basic linkages, 9,600 active decision-making components operating without any human supervision. That number appeared in preliminary industrial consulting reports. But within 6 months, it vanished from all official efficiency studies. Published manufacturing recommendations made no mention of the autonomous intelligence systems. The specific count of 9,600 control elements disappeared, almost as if someone decided that number raised too many uncomfortable questions. Because if American factories truly had 9,600 intelligent control elements operating autonomously, achieving quality and efficiency that supervised labor couldn't match, why would anyone accept the massive expense of hiring, training, and supervising large workforces? Why would industries commit to permanent labor costs when superior autonomous technology already existed? And most importantly, who benefited from suppressing the self-regulating systems? As documentation accumulated, another pattern emerged, one that researchers found profoundly disturbing. Despite being found in factories owned by different companies, producing different products built over a 30-year span, all the autonomous systems shared certain characteristics: standard pneumatic control pressures, consistent mechanical logic architectures, uniform feedback sensor designs. It suggested not just knowledge sharing, but deliberate standardization across a massive program. This wasn't organic technological development by competing inventors, it was coordinated implementation, possibly by a single engineering organization, with the resources to enforce technical standards across multiple industries and decades of equipment installation. The physical evidence from partially dismantled machines only deepened the mystery. Survey teams found manufactured components that didn't match any known American equipment suppliers, pneumatic logic elements with precision that anticipated modern manufacturing, mechanical memory drums with information density that shouldn't be possible with period machining, sensor arrays using measurement principles attributed to later scientific discoveries, assembly techniques that implied factory production of automation components on a scale that shouldn't exist for experimental technology. Some machines appeared deliberately designed to conceal their true sophistication. Autonomous control systems hidden inside what appeared to be conventional mechanical assemblies. Intelligence mechanisms disguised as structural components. Learning systems integrated into parts that looked like ordinary drivetrains. Others seemed intended for maintenance by technicians with specialized knowledge. Access panels requiring unusual tools, diagnostic interfaces for checking logic circuit operation, modular control elements designed for adjustment, and replacement by those who understood the underlying principles. Perhaps most disturbing was the systematic destruction schedule. The demolition of autonomous manufacturing equipment didn't happen randomly. It followed a coordinated timeline across all surveyed regions. Massachusetts factories dismantled their self-regulating systems in January 1899. Connecticut installations were removed in February and March. New Jersey equipment was scrapped in April and May. Different industries, different company ownership, different engineering contractors, yet all following the same destruction schedule, as if coordinated by a single directive. And the timing coincided exactly with new industrial safety regulations, promoted by equipment manufacturers and industrial management consultants. Not because the autonomous systems were dangerous. Accident records showed them to be remarkably safe, eliminating the human error that caused most industrial injuries, but because the new regulations specifically required direct human supervision of all production equipment and qualified operators for each machine, requirements that autonomous systems couldn't meet by definition, since their purpose was to operate without human intervention. It was regulatory elimination disguised as worker protection. And it happened simultaneously across multiple industries and jurisdictions that supposedly operated independently, promoted by manufacturers who directly profited from selling new equipment requiring human operators, and by management consultants whose services were only needed for supervising large workforces. When you study the final months of the 1898 survey program, something becomes impossible to ignore. The documentation didn't conclude with recommendations for studying or replicating the autonomous technology. It concluded with demolition orders and workforce expansion plans. Not optional upgrades, not efficiency comparisons, mandatory, immediate replacement of autonomous machines with supervised equipment. The deeper the survey crews documented the self-regulating technology, the more aggressive the elimination schedule became. Early reports that mentioned autonomous operation exceeding supervised performance were followed by revised reports emphasizing unsafe, unsupervised machinery. Equipment that initially demonstrated superior quality output was later required for immediate replacement with modern supervised systems. And this is where the final mystery begins. Because the most sophisticated systems, the most completely autonomous installations, the most obviously intelligent manufacturing technology, these were the machines where destruction was enforced first and most thoroughly. Factory owners who resisted found themselves facing labour union pressure to protect jobs. Engineers who advocated for preserving the technology were bought out by equipment manufacturers or professionally marginalised. In several documented cases, entire production lines were dismantled overnight. Work crews operating during shutdown periods, as if someone wanted the destruction completed before the autonomous capabilities could be widely publicised or analysed. The official explanation: worker safety, job creation, industrial modernisation. But if it was only about better manufacturing, why were demonstrably superior autonomous systems forcibly removed? Why were factories that wanted to keep their self-regulating equipment pressured into expensive workforce expansion? Why was technology that eliminated human error, improved quality, and reduced costs replaced with supervised systems that required constant labour expenses? It doesn't make sense from an engineering or economic efficiency perspective, but it makes perfect sense from a social control perspective. If industrial interests wanted to ensure that manufacturing remained dependent on large controllable workforces rather than becoming independent through autonomous technology that workers couldn't strike against, managers couldn't control, and that threatened the entire economic structure of industrial capitalism. Perhaps most telling is what happened to the machine components themselves. Unlike the assembled equipment that was scrapped, Some individual components survived, salvaged by workers, kept as keepsakes, or buried in factory foundations during demolition. This created a remarkable situation. Pieces of the original autonomous systems still exist, scattered in antique collections, engineering museums, and occasionally unearthed during industrial site excavations. They're typically misidentified as Victorian machinery parts or antique manufacturing equipment. But close examination by modern engineers reveals their true sophistication. Pneumatic logic gates that perform and not operations through air pressure. The same Boolean logic that underlies all modern computing, but implemented mechanically. Memory drums with precisely machined surfaces that store hundreds of bits of information through physical patterns. Sensor arrays that measure multiple variables simultaneously with precision that modern instruments respect. The components exist as physical evidence of autonomous manufacturing intelligence that official history claims was impossible before electronic computers. Industrial museums display them as mechanical curiosities. Engineering professors use them as examples of quaint Victorian ingenuity. But no one asks why they were designed with such sophisticated logic capabilities. No one analyzes how they could implement complex decision-making through purely mechanical means. No one questions what kind of machines would require computational components in an era before computation officially existed. Even patent records tell the story, or rather their systematic suppression does. Applications for self-regulating machinery didn't just get rejected, they were classified under provisions that didn't officially exist. Several inventors in the 1890s and 1900s filed applications describing autonomous manufacturing systems, mechanical intelligence circuits, and self-learning machines. These applications were immediately transferred to restricted review and never returned to public filing. Inventors who inquired received letters stating their inventions conflict with public policy or duplicate restricted prior art. But the prior art was never specified, because acknowledging it would mean admitting the factory autonomous systems existed. Several of these inventors died under circumstances their families found suspicious, one in a factory accident while demonstrating his system, another in a workshop fire that destroyed his prototypes, a third who simply disappeared after meeting with government officials about his patents. Others accepted substantial payments from equipment manufacturers and signed agreements never to pursue autonomous machinery research. A few who persisted found themselves unable to get factory trials, their professional credentials questioned. Their other inventions mysteriously denied patent approval. The campaign to suppress autonomous manufacturing technology wasn't subtle. It was comprehensive, coordinated, and ruthlessly effective. And it succeeded so completely that most people today don't know truly autonomous machines existed in the 1800s, let alone that they operated successfully in factories for decades before being systematically destroyed. Even the evolution of industrial employment tells the story. Factory workforces actually decreased from the 1850s through the 1880s as autonomous machines became more prevalent. Fewer workers needed because machines ran themselves. Then suddenly, in the 1890s, 1910s, factory employment exploded. Not because production increased proportionally, but because autonomous machines were replaced with supervised equipment requiring human operators. The industrial workforce boom wasn't driven by technological progress. It was driven by technological regression, the deliberate replacement of autonomous systems with labour-intensive supervised manufacturing. Why was the most extensive evidence, the most sophisticated technology, the most economically transformative innovation suppressed and destroyed? Because when you step back, the pattern becomes clear. The mechanical logic systems were destroyed. The pneumatic computing elements were destroyed. The 9,600 autonomous control components were scrapped. The factory-wide intelligence networks were dismantled. The machine learning mechanisms were demolished. The production records were reinterpreted. And even the inventors' careers were destroyed, almost as if the survey program had accidentally revealed a chapter of automation technology that wasn't supposed to be acknowledged. A chapter that threatened industrial labour systems. A chapter that suggested autonomous manufacturing was achievable with 1840s technology. A chapter that showed factories could operate with minimal human supervision, eliminating the vast workforce that gave industrial capitalists their economic and political power. The 1898 factory reorganizations weren't just industrial modernization. They were targeted elimination of technology that threatened the entire structure of industrial society. Because if mechanical artificial intelligence worked, and the factory records prove it did, then everything that came after, the entire edifice of supervised manufacturing, labour management, and industrial employment, was a socially motivated regression disguised as progress, and fragments remain in museum collections, antique shops, and buried foundations. Components of mechanical computers, pneumatic logic circuits, autonomous control systems that operated successfully without any electronic or computer technology. Physical evidence that they built self-regulating machines in the 1800s, not through impossible engineering, but through mechanical intelligence principles that challenged no natural laws, only social and economic ones. The systems worked, the evidence remains. And we've been told that autonomous manufacturing required electronic computers, that artificial intelligence needed digital systems, that self-regulating machines were impossible before the computer age, not because the engineering was impossible, but because admitting the truth would mean acknowledging that autonomous production was deliberately destroyed to preserve industrial labour systems and the power structures they supported. Thanks for watching, and if you found this interesting, well, there are a lot more suppressed technologies with stories like this. Maybe I'll see you in the next one.